Alright guys, so the last section in Unit 4 is 4.5, which is going to be graphing the derivatives and the antiderivatives from the graphs. Okay, so this first little section is starting with the actual function and then taking the function and then drawing its derivative. Okay, so things that we're going to think about is we're looking for the slopes and specifically critical values of our original function. Okay, so remember the first derivative is just giving us the slope of the original function. Okay, so for starters, the first thing that we want to realize is values where the slope is 0. Okay, so those are going to occur at maximum and minimum values. Okay, so we have a maximum or a slope of 0 when x is -2. So if I go to my derivative, that would be when my slope is 0. Okay, as well as when I have a x value of 2. Okay. This function is starting at about 3.5. Okay, and from here to the first spot, it has a positive slope. So if you kind of estimated the slope maybe at this spot, I would say that the slope would almost be like a +2 almost, maybe just slightly less than a +2. Okay, so at 3.5, if the slope is +2-ish, I would say that it starts there. Oops, right about there. Okay, so you can say, or you can see that there, each time we go a little further. Okay, so now if you're kind of looking at the x value of 3, okay, the slope is getting slightly smaller and slightly smaller every time. Okay, so it's going down, down, down to this value. Okay, another critical spot that we want to look at is probably right about here, right at the cross. You can see that this is a point of inflection from the original graph. So we can look at the slope of it, and I would say that this looks to me like it would be about at -1, right at that spot. So when the x value is 0, I'd say the slope is about -1. Okay, and then the other critical spot is going to be here at the end. Okay, where now we've got a positive slope, and I would say it's about the same as this one over here at the end. So at 3.5, we're back up to almost 2, I think. Okay, so another thing to think about when you're graphing the derivatives of a function is, what does the original function look like? Okay, so to me this looks like an x cubed function that just happens to be bounded. If you were going to derive it, you would basically get something that's x squared. Okay, so I mean, if you wanted to be really technical, you'd have a 3x squared. But if we ignore the slope completely, that's going to give us the shape of our derivative piece. Okay, so we know that this is going to be like a parabola. It's going to stop at these end spots, and it's going to curve down. So it's going to have a gradual slope, very parabolic. Okay. All right. So the second half is going the other way. Okay, so the antiderivative is the idea of, here is my derivative. So if I was given this piece over here, can you come up with the original function? Okay, so things that are going to help you with that are using the number line, like what we did in the previous section, using the derivative and the number line to kind of produce that original function. And then the second derivative, so using the second derivative as the slopes to figure out what the concavity is of it, of the function. Okay, so for example 2, okay, this time they're giving us the derivative function. Okay, so to go backwards and go find the original function, what I'm looking for are critical values. Okay, so a critical value is any place where the derivative is 0. Okay, so the derivative is 0 when it crosses the x-axis. So I see 1, 2, 3 critical values. Okay, so it looks like this crosses at negative 3.5, 0, and positive 3.5. Okay, and then I'm going to just use the slopes between those values to help me draw this. Okay, so up here on this side between 3.5 and 0, it's above the x-axis, so that's a positive slope. And then between 0 and 3.5, it's below the x-axis, so that has a negative slope. Okay, so you can kind of imagine that we have this something going up, something going down. Okay, so what happens at 0? Okay, at 0, and specifically 0, 1, because that was given to us, we can say that there is a max at 0, 1. Okay, and then it goes down. Okay, so now to figure out the shapes of these curves, we can use the concavity. Okay, so to figure out second derivative, that's kind of like almost going backwards to what we did on this piece up here. Okay, so the second derivative is going to come from the slope of the first derivative. Okay, so any place where the slope is 0 of my second derivative is going to be a critical value. So I have slope of 0 at negative 2 and at positive 2. Okay, so then again to figure out the concavity. Okay, so I'm looking again at the slope. So if you're kind of looking on this side, we have a positive slope when we're left of negative 2. Between negative 2 and positive 2, the slope is going down, so we have a negative slope. And then from 2 back to 3.5, we have a positive slope. So this is giving us the concavity of our original function. Okay, so the next thing that I kind of want to consider is what does the shape of this graph look like? Okay, if this shape is kind of looks like an x cubed, what is my original function? Okay, so thinking that you're going backwards, okay, up here, when we went to the derivative, we lost an exponent. Okay, if we're going backwards, we're going to add 1 to the exponent to get back to the original function. Okay, so this function should be something to the 4th power. Okay, so it should kind of have a parabola effect. Potentially it could have a couple maxes or a couple mins. Okay, because of this piece right here, I know that it's like an upside down parabola, and since there's only one min value, it's just basically like a parabola type of thing. So I can graph my max point of 0, 1. Okay, and then basically at that point, that's all of the exact values that I have. After that, it just kind of becomes estimating the slopes. So when I go to the left of it, I know that I have this positive slope and negative slope, but at negative 2, we have kind of a happy face and then a sad face. Okay, but I don't know exactly where that happens. So I'm just going to kind of say the middle of the graph here looked at 0, so I'm just going to kind of center it at 0. So I'm going to have a point of inflection, so I'm going to kind of happy face. And then between negative 2 and positive 2, I have a sad face. Okay, remember sad face up to my maximum. Okay, and then past positive 2, I have a happy face. Okay, we're going to about 3.5 there, so we should stop where that other function stops as well. So this one kind of has, you can see the next to the 4th kind of look to it. There would be more on the ends for this to see what happens in the end. But the same idea. Okay. So then they go a little bit further. Now you're using your derivative this time to graph your original and then also graph your second derivative piece. Okay, so the first thing I'm going to do is do my number line with my first derivative. Okay, so critical values are any place where it crosses the x-axis where the first derivative is set equal to 0. So I have a critical value at negative 2. Okay, so basically I'm going to look at that and say the slope to the left is below the x-axis, so I have a negative slope, and then above it I have everything is positive. Okay. When I go to my second derivative, I'm looking for any place where the slope is 0. Okay, so there's kind of this weird wiggle here at this spot. So that's going to be a critical value on my second derivative at 2. Okay, so second derivative, I am looking at the slope of the graph. Okay, so the slope of the graph for this is always a positive 1. Okay, so we have a positive, and then for here it's always positive, although it is changing, it's still positive. Okay, so kind of what's happening with this function is it looks like it's a piecewise function. There's two different pieces. There's this side, and then there's this side of this potential function. So I'm going to go straight to the second derivative and using the slopes of this. So from negative infinity to the x value of 0, it has a slope of positive 1, and it's always a positive 1. So I can just graph that right here. And I'm going to put a circle at 0. Sorry, that was not a very good circle. Here we go, right at 0. Because it's not differentiable here at 0 because it is kind of like a sharp turn. It's not smooth. Okay. But if you kind of look on the right side of this, it looks like this could be like a bottom of a parabola type of idea. So it starts out with a slope that's almost 0. So I'd go to 0, and then it gets positive and positive and positive. So it's getting bigger and bigger. So I would draw a slope of up 2/1, I think, just because I can use this value right here. And let me just kind of erase all my blue marks. Right at 1. Okay, so this slope at the x value of 1 looks about like a slope of, I didn't draw that very good, but I would say it's about a slope of 2. There we go. There we go. Okay, so roughly about a slope of 2. This could be give or take a little bit there. All right, so now if I go the other way and come with my original function. So sometimes I again think that you could say this left-hand side, if you were going to write the equation for it, would be positive x plus 2. The blue piece could be, it looks like x squared parabola plus 2. That's up 2 units. Okay, so if you kind of think about using that information and going to your original function, remember you're going to gain an exponent. Okay, so this linear piece is going to become like a parabola. Okay, and it has a, from our number line, down, up, okay, it has a minimum value at -2. We can't really say what the corresponding y value would be, so really you could move this up or down. I'm just going to throw it at 0, just makes sense in my mind. Okay, and then it's going to kind of be a parabola, and it's going to come back up probably about there. Okay, so at, oh, whoops, I screwed this up right here. This should be a 0, excuse me. Okay, the y value is 2, I was looking at that spot. So from there, okay, then I want to be thinking, okay, this is going to have, add 1 to the exponent, so it's going to kind of have a John Travolta-ish look. So it was like linear, and then now the slope kind of got steeper and steeper and steeper of it. So it's going to be a concave up, so it's kind of a happy face, which agrees with what it was before, but it's going to be a little bit steeper. So it's going to be kind of like a John Travolta right arm that comes out of this, off that other side. Okay. So it's kind of interesting the way this all works. We can't come up with exact values if we don't have points on the graph from the original, but I mean, really up or down, this could be moved, but you kind of have a rough guess without exact values. So if we move through the assignment, which I would like for you to do, these first 8 questions. Okay, so we can have the first 8 questions done by Monday or Tuesday, whichever day I see you next. That would be good. Okay, so I'll do a couple of these with you. They're not too hard. Number 1. Okay, so for question number 1, it says to sketch the graph of the derivative. Okay, and so this piece that is given to us is the original function. So we're looking at the slope of the graph, any max or min you might see. Okay, so for question number 1, there is no max or min. It's just a straight line. It has a constant slope. So the slope is up 3 over 1. So that's very simple. The derivative is exactly 3. Oh. So 1, 2, 3, that would be a horizontal line. It's always going to be 3 on that derivative. Okay. So for example, number 2, this one is an x squared function. Okay, so we know that the derivative would be linear. We have a max, or excuse me, a minimum value when x is 1. Okay, so that just means that it's going to cross the x-axis at 1, 1, 0. Okay, and basically from there, the derivative, since the derivative would just be a straight line, would be basically it would have about a slope of 2, positive 2. Okay, so this f derivative, and then if you kind of think about what you're graphing here, between -1, oh, I guess these do have endpoints, so I should technically not draw arrows and instead draw endpoints. So we're going from -1 to 3. So there we go. Okay, so the slope of this has a negative slope down from -1 to +1, which is below the x-axis, and then a positive slope above it. Okay, so that's kind of what you're graphing. Okay. Question number 3. What is the slope of that whole line? The whole slope is horizontal. Slope of a horizontal line is 0, so 0, boom. That's pretty easy. Okay. For question number 4, okay, we have this absolute value graph. Okay, it has a maximum when x is 0. Okay, and then on this side, when values are less than x, it has a constant slope of 1, up 1 over 1, up 1 over 1. So the slope from -infinity to 0 is just 1, so we can draw 1. And again, this is not derivative or differentiable at 0. I'm going to draw a hole. And then on the right side, it's negative, so it goes down again with the slope of -1. So this one would be at -1 on that side. Okay. So for question number 5, and I'm not going to do all of these, but I'll keep going. Okay, so this time they're giving us the derivative. Okay, so what we have to do is graph the antiderivative. So we have to go backwards and graph the original function. So these are all derivative pieces. Okay, so what we're looking for is where the derivative is 0. So I think this one helps to have a number line when you do this. So it crosses the x-axis at 0. Okay, the slope from the left side is above the x-axis, so it's positive. On the other side, it's negative. Okay, so if you kind of look at this, this looks like so. since the original function is kind of a negative x, remember when you go to the original, you add 1 on the exponent. So I know my next one is going to be a negative x squared. I have a maximum at 0. And since I actually have a starting point at 0, 0, I can be a little bit more precise in my graph. I can say exactly at 0, 0, I have a negative parabola. Okay. Alright, so for number 6. Okay, so this one is also a negative x squared. It's been moved up 1, so you could even say up 1 to kind of give you a little bit more something to look at. On my number line, I have 2 critical values, 2 places where it crosses the x-axis, one in -1, one in +1. So when it's -1, I have a negative slope because it exists below the x-axis. And then from 1 to 1, -1 to +1, it's above, so that's a positive slope. And then it's below, so that's a negative. So this one, let's see, down, up, down. If I add 1, is going to be a John Travolta, which should make sense. If we add 1 to the exponent, it would be a negative with his left arm up. Okay. Another critical point that we should look at is the maximum. Okay, so this is thinking about, so this is the first. You can use in the second number line for your second derivative to help with concavity. Okay, so if you have a max at 0, you have critical value for your second derivative. Okay, so now for the concavity, you're looking for the slope of the derivative. So from -2 to 0, it's going upwards, so that's a positive slope. And from 0 to 2, it's going down, so that's a negative slope. So that's the concavity. So we've got a happy face and a sad face. Okay, so we got a starting point at 1, 2, 1, 2. Okay, and if we think about 1, what it was in our function, 1, 2 is this piece right here, this relative max. So 1, 2. Okay, so we could kind of say we don't really know how far it went down to get to -1. All I can tell you is that it went down. So we could even go, I mean, I could really center this and go boom, boom here. And I do believe this function stops and starts between -2 and +2, so we want to be consistent with that. Okay, so I have this curvature, this happy face, till we get to 0. We'll just center right there. So we'll go boom, and then we have a sad face because there's another max. It goes down to 2. We'll say that's 2. That's -2. So it should kind of have a John Travolta look with his left arm down. Sorry, that looks bad. There we go. Perfect. Okay, so I think for the most part I gave you something to go on, so go ahead and finish 6 and 7 on your own. Just a heads up, so as a kind of a thanks for watching this video, I'm giving you a heads up that there will be a quiz on Monday and Tuesday. This quiz I put on to OneNote. Okay, it is right here, so for those of you guys who want to take a look at what you're going to have as a quiz, here it is. Okay, and I'll even kind of go over a couple of these. Okay, so this is basically graphing the function using your first and second derivatives to find maxes and mins and concavity. Okay, so I'm not going to do all of this. I'll kind of run you through it. So the first part is x and y intercepts. So to find the x-intercept, you set, f of x, or I guess in our case right here in this example, y equal to 0. Y equal to 0, and solve. Okay, so this one isn't going to have an x-intercept because it's going to exist. It's going to be a parabola above the x-axis. To find the y-intercept, which you should find, you let the x equal 0, so that will be one point on the graph that you can find. Asymptotes, any value that makes the denominator 0 as an asymptote. This is an x-squared function. It is a parabola with no asymptotes at all. Okay. So now to find critical points. So critical points is coming from your first derivative. You might want to rewrite this function for some reason. I bet that throws a lot of people off, just that way that was written. So your first derivative piece is how you find maxes and mins. So 1/2 times 2 is 1, so you get x plus 1. And to find your critical value, you set that equal to 1. Okay, so then once you have your critical values, which in this case happens to be -1, you're going to do your number line test, okay, for the slope. Remember, first derivative gives you slope. Okay, I'll let you do that. So it's going to be a positive and a negative, or a negative and a positive. Then the next part, it asks you for concavity. Okay, so concavity comes from second derivative. If we take the second derivative of this, we get 1. Okay, so this is one where, remember, for concavity, you're only looking for positive and negative values. Since 1 is always positive, this function has a positive concavity always, okay, which is a happy face, which makes sense because it's a parabola. Okay, so I bet you can figure out just from that what the minimum value is, and you should get a pretty accurate sketch from those. Okay. Now this one is a little bit more fun, okay? Basically the same sets are going to happen, but you're going to have some more stuff going on between here and here, okay? Okay, so question 3 and 4 are exactly like what I just did on the notes today, okay? So really take into account, if I'm given an f of x and this looks like a John Travolta, if I derive that, what's my next function going to look like? So if I have something x cubed, I'm going to lose one in the exponent, so this is going to be look something like x squared. Okay, so remember that you're looking for maxes and mins is on your first derivative. Okay, that will help you draw that. Okay, and then vice versa, you're kind of going the same way. If this is a linear function, what is your original function going to look like? Remember, this is the derivative, so if we go up, you're adding an exponent. What is that going to look like? Okay, so remember, places where it crosses the x-axis is going to be where your derivative or your slope is 0, which tells you a maximum or a min. All right, that should be enough. 30 minutes of very educational math and enough information to help you nail the quiz on Monday or Tuesday.